Hey, it's George Leoniak. I'm here with another video for New Geometry, and I'm going to do a little bit of a follow-up on my previous video, which had to do with entitled "It's Sacred Geometry at All Scales, Thank God." And in this video, we are going to look a little bit more at the Earth grid, which I described in that video as being related to a form called the Pentacus Dodecahedron. And in my week, I made some more discoveries related to these forms, and that led me down a whole nother train of reasoning and looking at a lot of Buckminster Fuller's work and elaborating on some of his designs. So, as normal, I'm going to go into the screen share here. I have a couple other web pages that I want to show you. But let's get started with the screen share. And this is really going to kind of lead up to a kind of a new discovery and a new way of looking at things in relationship to the Earth grid. So let me share the screen. All right, so, this is kind of where we're headed. I put this slide first because I just did this artistic rendering. And of course, the power of these visuals, this artistic expression that comes through, all the mathematics and the geometry that's associated with this can be highly decorative and psychoactive in terms of connecting to the forms in other ways. So definitely it could be a meditative experience rather than just a purely geometric mathematical one. Let's just back up a little bit into my previous video and look at where I was headed with that one, because, this is in Google Earth. This is the universal vector grid that has been transposed over the Earth, looking at a lot of the ley lines. And this is 15 great hoops that are around this. And this is the Rhombic Triacontahedron here, which is often associated with the Earth grid that fits over top of a lot of these vertices. Match up to a lot of the vertices on there. That's not fitting well, but I'm going to explain to you why I was led to the Pentachus Dodecahedron, because I saw that the vertices, there was this flat gap here between the vertices where it would be touching the outer edge. It's many of these places, this vertice, for instance, should be up and touching this outer, or could be touching this outer sphere here. So this one allowed for a lot more of the vertices to be touching the outer sphere. So, I was like, okay, that's great, that's cool. I figured out how to draw it in sacred geometry. It's kind of a bit of an upgrade, I was thinking, to the Rhombic Triacontahedron. The Rhombic Triacontahedron, of course, is still in there, but now we're adding some additional vertices to it. So this week I decided to, I never really did this before, but I said, well, let me do a little more research on this Pentachus Dodecahedron. And I decided to put the, I took one from Wikipedia and I took my drawing and I placed it over top of the Wikipedia drawing. And I was like, oh no, what's this about? The vertices that I have don't all line up perfectly with the one that's on the Wikipedia site. So I was like, oh no, does that mean I have to go back and, redo the whole video or explain why it's off? So I couldn't quite understand it. But then when I went to another site, I realized that there's a version of the Pentachus Dodecahedron, which is called the biscribed version. So I clicked on what the biscribed version was, and the biscribed version is actually a Pentachus Dodecahedron, which has all of the vertices touching the outside surface of the sphere. Well, that, of course, is exactly what I was planning on. I was hoping that all 32 vertices would be touching the outside of the sphere. Now, the regular Pentachus Dodecahedron doesn't display that. Some of the vertices are, let's say, just sunken in a little bit. But this biscribed version, all of them touch the outside surface of the sphere. That's going to mean one thing for the, in that video, that the carbon 60, where I finally come to it after the Pentachus Dodecahedron, this is the truncated icosahedron here, and that would mean that the vertices would be slightly different with a biscribed version, and there is a biscribed version of this truncated icosahedron as well that's in relationship to the Pentachus Dodecahedron. So it's just good to note that there's another version, but I want to just show you really quickly, stop the share there, and just show that this site where I found this, because you might want to geek out a little bit at this site. It's DeMacui. Okay, now this site, let me just show you the main menu here, has just got just about probably every type of solid polyhedra form, just all the Archimedeans, the Platonic solids, the Catalan solids, there's quasi-irregular polyhedra, self-intersecting, versi-quasi, you know, a lot of things I haven't even looked at. I mean, I'm not sure what a lot of these things, what a lot of these forms are, different variations of some of the base forms. But on his page, or on this page here, you know, look, it goes on and on and on. I happen to come across that there are biscribed, two biscribed tabs here. And one is the biscribed non-chiral forms, solids. So the non-chiral is just kind of a fancy word for like, are they mirror images or not? And just to show you, like most of the geometric forms that we look at, like the Platonic solids, for instance, are all non-chiral. The non-chiral forms are ones that aren't self-mirroring. So here is the biscribed chiral solids, which I'm not going to really spend much time with, but you could see that they they have some irregularities to the vertices where they aren't mirror images of one another. So if you folded it over on top of one another, they aren't going to just perfectly match up. But there are quite a few of these biscribed versions of these chiral solids. But let's just go back to the non-chiral biscribed. Now, there's only 4. These are all the duals up here. So there's 4 basically. There's 8 on this page, but there's really 4 because each of these have a dual. For instance, this biscribed Tetraxus Hexahedron, this biscribed truncated octahedron, it appears to be the dual of that one. I think that's correct. Let's see. Does it have a dual? Yep. Biscribed, the dual solid is the biscribed truncated octahedron. So I know I'm going off a little bit on this, but I just wanted to let you know that this page exists. And the cool thing about this page is we can go to, here's our Pentachus Dodecahedron. And here's a little thing to note. If you want to look at it as if you're looking at it just flat on the page, just line that little slash up with the circle. So that's what it would look like if it's flat on the page. And then you have the ability to rotate the form all the way around. So this one is what I wound up drawing, was the biscribed version of the Pentachus Dodecahedron. And for instance, here's the other version of it. And I'll just show you that it's not going to have all the vertices lined up. So this is the other version of it, and the biscribed, all the vertices will not be touching the edge of the sphere. So for some reason, I was just gravitated towards and being led to creating and working with a lot more of the biscribed forms. And I'll tell you why, because there's only a few forms out of all this big list that I'm showing you here, of all these Archimedean Catalan solids that happen to be biscribed forms that are of the non-chiral variety, which we're going to look at. Only 4 of them. The Tetraxus Hexahedron can be biscribed, Dystacus Dodecahedron, and the Dystacus Triacontahedron, and of course the Pentacus Dodecahedron. Well, all of these other three forms right here are going to be becoming very much important into where we're headed in the next few slides. I didn't realize it at the time, but a lot of the forms that I've been working with and creating are of this biscribed nature. And I believe that they're kind of like the next evolution of the Platonic solids, because there's the five Platonic solids themselves are biscribed solids. So these other ones are also biscribed solids. So it just so happens, because you could put all vertices on the outer edge of the sphere as well as out of the edge. The inner sphere also has, inner faces will also have a sphere within it. So the five Platonic solids do that, in addition to these other non-chiral forms here. So in my mind, that marks them as having some sort of, stands them out from the other ones, and I'm going to show you why that appears to be the case in the video here. So I just want to show you also, you know, there's a lot of different ways to explore the sacred geometry, and they're also really looking at dice. Of course, all five Platonic solids are dice, but there's a company called the Dice Lab which makes these dice that you know, I was getting at the time, because they have the 120-sided form. They also have the Pentacus Dodecahedron form as well. So they have a number of different forms available that are, here's the Triacontahedron, Rhombic Triacontahedron. So here, for instance, is one of the 48-sided forms. This is the Dystacus Dodecahedron, but these aren't biscribed. You see, these peaks here aren't going to match these peaks. And what we're going to be doing in our video is creating biscribed forms. And I was doing this with a lot of the little models that I was making. For instance, this is a 48-sided piece compared to that 48-sided piece. And this one here, I did this a couple of months ago, is biscribed, meaning that all the vertices that make this up are all going to be touching the surface of a sphere, where this, only the octahedron that's within this are going to be touching. So only 6 out of the vertices rather than all 26 vertices. Same thing with this Tetraxus Hexahedron here. This one is biscribed, meaning that all the octahedron and cube edges are going to be touching the surface, whereas this is what the Tetraxus Hexahedron looks like when only the cube edges are touching. So it's just slightly inflated. So that's just where we're headed. I wanted to give you a bit of a 3D representation of what these forms are going to be looking like when we get back to the slides here. So let's continue on. Share the screen. Here it is. Okay, so now that we kind of looked at these biscribed versions a little bit, let's just go on with how was that Pentacus Dodecahedron? How did I create that? Well, I'm pretty sure I described in the other video what I did to do this was I took a dodecahedron and I took an icosahedron, and instead of them having being a compound of one another where the two bars meet each other in the middle, for instance, this blue line would intersect that and they'd be touching. That would be a compounded version of those. I decided to pull that icosahedron in and make it smaller so that it would actually, the surface of the icosahedron vertices would then be touching the sphere like that. So then what I did was I've just connected the dots, and after doing that, I came up with the biscribed version of the Pentacus Dodecahedron. It's essentially created out of this dodecahedron and icosahedron in a biscribed version. Now, all the images that you're going to see here, you could pretty much just think of as having a cube within this dodecahedron that is 1 inch, which means that this distance from this vertice to that vertice is √3. So that's 1.732. So all of these spheres in this is going to be 1.732 or √3. So it's just a very important number in sacred geometry, the √3 number. It's what happens when you do the Vesica Pisces, you get a √3 measurement. So everything in this is going to be scaled to a √3 sphere. So this Pentachus Dodecahedron, all the vertices within it would be touching that sphere. So, you know, when we have this Pentachus Dodecahedron, what I also did in the previous videos, well, I said, well, let's put that over top of the Earth. And I don't know if anybody watched that video who's watching this now, they might have saw me even stumble a little bit in the video because I realized at that moment that, yes, I mean, I'm creating some more of the sphere, the edges of the sphere, the hoop that would go around there. But I also realized that this yellow one here that I have, for instance, going from here to here, cuts across and isn't actually completed, which means that there's a vertice from this bar to that bar, which this edge right here is still, let's just say, sunken in because there's not a vertice that's actually poking up here and actually touching. And of course, this is the main vertice we've been interested in, and that has to do with where the pyramid is roughly situated. The Great Pyramid of Giza is roughly situated right at that location, which is UVG1, and that yellow arc is going right over the top of it, and there's no vertice there associated with that. So earlier this week, I was like, I wonder what is going on there. There must be some other form inside here that is going to, let's just say, inflate these other locations which are sunken on the Pentachus Dodecahedron. So I, found out that that form is the Icosa Dodecahedron. So right now we're going to create a new form. It's, a new form for me, and how I'm doing it is the dodecahedron plus the icosahedron plus this Icosa Dodecahedron. Now the thing about this Icosa Dodecahedron is that all those vertices are now going to also be touching the √3 diameter sphere. So we want to get all those measurements lined up so that they'll be touching the outer edge of the √3 sphere. So this is kind of right over here what the inner dynamics, the inner drawing of the, let me just change the scale here. So this is what the inner drawing of all those together. And, I have to go into these drawings and find them, because the way I do a lot of this work is really from a 2D perspective. I don't have a software that allows me to draw it and then just rotate it around to see what it looks like. I've got to find all these vertices and make sure the measurements are all correct. But so I was able to overlap and do the drawing, connect all the vertices, and what comes out when I'm done with that is the biscribed Dystacus Triacontahedron, which is also on that Makuni site, which has all those biscribed forms, at least the 4 biscribed forms, plus the duals of each of them. So this is the Dystacus Triacontahedron is this big 120-sided die that I was just showing you. But now the thing about it is that icosahedron, which is so sticking up at the 12 vertices, is now been pulled down into the √3 so that all the vertices are now touching the outside of that surface, which means that is 62 vertices are in contact with the outer surface, giving us 120 faces of that form. So, the Dystacus Triacontahedron is kind of like the biggest polyhedron that that we can make of the Archimedean solids that has 120 sides. Besides when you get into like geodesic domes and things like that, which can have quite a bit more. But when we follow the kind of progression between the Archimedean Catalan solids, this is the kind of culminating 120-sided form. So I was like, great, now I can go back to Earth, the Earth grid, and now I'll be able to put this fully, all the vertices represented, because now I've included the Icosa Dodecahedron to relate to, let's say, at least that one UVG1 near the Great Pyramid. That will now be, let's just say, touching the surface rather than being sunken down. So I went through one progression from that Pentachus Dodecahedron now into this Dystacus Triacontahedron, the biscribed version of it. So now that will, as I'm showing here, fit, over top of that Earth grid. Now remember, this is a spherical model, and these vertices of these lines won't match up perfectly because we got, this 2D image here where these are meant to be curving around. So there's slight differences when I lay these over top, but all the vertices on a curved surface would match these Dystacus Triacontahedron. Excuse me. So there are 15 hoops, let's just say, that are created just from going over the top of the surface of connecting vertices as we go. There will be 15 hoops or 15 great circles. And now this is where I want to just start to get into Buckminster Fuller's work. Because a while ago, in one of my previous videos, way back there, which was along a similar track as this video in terms of looking at the unified forms as they build off of one another in sacred geometry. Well, through that study, I came up to Buckminster Fuller's 31 great circles, which he took 3 forms and put them together to do essentially kind of what I'm doing, is connecting vertices and then creating these hoops around the outside, which he's calling great circles here. So the way he did that was he used the Dystacus Triacontahedron to get the 15 great circles. Now, his Dystacus Triacontahedron is just the one, it is not biscribed. So it's only going to give you the vertices of the icosahedron. So, I mean, essentially you could have just put the icosahedron in there. But, this one is giving you the edge that looks like it's touching. But remember, the only thing that's touching here is this vertice and this vertice and the vertice that's further on down here. It's not actually this one in the middle. It gives you the apparent shape of the form, but it's not going to actually be touching because it's not a biscribed version. I've got the biscribed version in what I've got going on. And also, he included the Icosa Dodecahedron. Now, of course, I did that too, and that gave you 6 more great circles. And then this form always kind of freaked me out a little bit, and I was like, "Wow, how did you get there, with this one, this dodecahedron, the 10 great circles?" Well, essentially, it's like a double dodecahedron, a double decker, and then he put that one in there and came up with the circles. Well, I believe with just on alone with the biscribed version of the Dystacus Triacontahedron, that alone, just this, gives you all 31 great circles, and you don't need to do a double-decker dodecahedron. And the Dystacus Triacontahedron, when it's biscribed, will include the dodecahedron, irregular dodecahedron, the icosahedron, and the Icosa Dodecahedron, like I showed you before. I'll show you those images again in a second. So these are not super precise down here because I just bring these highly precise drawings into PowerPoint, and then I just kind of draw in the arc as much as I can because I don't have a software that does a nice arc. but I just kind of follow and connect the dots because I know all these vertices are touching, so this should make a nice hoop that goes along. So we know that this Dystacus Dodecahedron here, because it's biscribed, we will create the 15 hoops easily. So we've got those. And we also know that just our dodecahedron that's in there will also, when we follow those lines, we'll create these stars because those vertices are all touching. We'll now create 10 more hoops. So we've got the 25 hoops. And of course, we added the the Icosa Dodecahedron into it. So we've got 1 hoop, 2 hoop, 3 hoops, 4 hoops, 5 hoops, 6 hoops. So we got the 6 more hoops, and we got the 31 great hoops, the great circles, just from one form. Dystacus Dodecahedron pretty much is all you need when it's biscribed. All those vertices are pulled in, and then we've now created the 31 great circles of Buckminster Fuller's work. So that was just a start for me when I realized how simplistic that was, that with those 3 forms that I'll show you here once again, pretty much the icosahedron, even though these aren't great hoops because you're missing it, it does give you the vertices that you need to create the 15 great hoops. When you add the dodecahedron in, 10 hoops, and the Icosa Dodecahedron gives you the additional 6. So I said the same thing again, but now you could see the forms as they're associated with the internal dynamics of those hoops. And then you don't need the double-decker dodecahedron, and the icosahedron is pretty much not the final form is the Dystacus Triacontahedron, which includes these 3 forms. It's not just one of the forms because those points only correspond to touching the vertices of the icosahedron. So we have to biscribe all these 3 forms, and then we get the 31 hoops. I believe it's a better method than the one that was used by Fuller. But hey, he's a big name. I don't want to step on any toes. He's phenomenal, and I love all his work. But I believe in sacred geometry, regardless if you're a guy like me, living in the woods, or Buckminster Fuller working at a university. We have to continue to push the limits of our understanding and relationship and bring sacred geometry further, as Buckminster Fuller did with his work. We can continue to expand with the current researchers who are out there adding to it. Continue to take it further, not just for our own sake, but for the future generation's sake, of how we continue to expand this knowledge and grow upon it. It's not just completely fixed in stone. Yes, certain mathematics and certain shapes and certain images, the Platonic solids, you can have these certain angles that show up. But when we combine them and put them together and look at things in new ways, we advance our understanding of these forms and open up our experience to new technologies, or building new things, or learning more about our own biology and DNA, etc. So I'm going to continue to do that in this video, and just see where I go with it, and show you where the path took me over the next few days after making that discovery. So the first thing is, like, if you like connect the dots, this would be fun to print up, because in this little connect the dot scenario here, these are all the points that give you those forms. So if you could see the pentagon shape here. So that would be the dodecahedron. The icosahedron is the blue ones, and the white dots are the Icosa Dodecahedron. It's kind of neat just to see them like in that way, but this is how we add up to all the vertices, the 30, the 20, and the 12, which will give us the total of the 62 vertices. But I still felt like there was something missing in there, like it wasn't completely filled out. But I decided to play connect the dots for a little bit, because the thing I like about this view, and just to back up, Buckminster Fuller was doing sacred geometry, but when you look at a lot of his work, at least in my mind, and at least the way I've seen things presented, is like you have all these geometries, like on the Mikuni site, the DM Mikuni site, that has tons of forms. And then you have like, what's sacred geometry? And sacred geometry is like, in most people's minds, the flower of life, the Platonic solids, and stretching the limits to the Rhombic Triacontahedron. Yet there's this whole expanse that other researchers have been looking at, And then there's this kind of like a divide between like, well, we don't know how to draw that stuff, so how do we incorporate that into sacred geometry as we understand it? So we got to create at least, a bridge. What I'm working on, creating a bit of a bridge through those more expansive forms up to like 120 side forms, all the way back down to the tetrahedron, which is, the four-sided form. So with these connect the dots, and of course, in my video, the Phi Yantra, all these images that I'm showing you here are all contained in the Phi Yantra. I was able to draw all this stuff in that form. So now we have this this drawing technique that allows these other forms to be manifested in our artistic expressions, which there further infuses the kind of scientific mathematical geometric discoveries into a way that people can relate to this artistic expression and have the sacred geometry be the link kind of between the two of the science and the art. Okay, so we have the square, and I like this view, as I've said before, because right off the bat it gives me two views of the cube. One is the straight on square face of the cube, so of course that's got some depth and volume to it. And then I also have this other tilted view, which actually gives me the √3 measurement, because this vertice of the cube is here to here. So I know that this cube is, if I stood it upright, it would be standing on its vertice directly up and down on the axis, because it's touching both ends of the sphere. So each of the dodecahedron is made up of 5 cubes. And I'm showing 4 of the other views besides just the regular square in this. And all it is just basically mirror images of one another. I've rotated one, I flipped one horizontally, I flip it vertically, I flip it horizontal, I flip it vertical, and then I have the other 4 views that are showing up. And when you combine all those together, well, that's what creates the pentagram inside of the pentagon shape. So every time you see a pentagram, just a regular flat pentagram, you could envision in your mind that that's just the edge of one of the 5 cubes. So all 5 cubes are contributing to one edge of the pentagram. Okay, the dodecahedron is in that. And the other form in this that we're building up towards something here, but in here we have the tetrahedron, which we know in each cube there are 2 tetrahedrons. So we have just this one tetrahedron, which of course looks like a square, but this little dotted line in the back is actually behind this edge here. So it's a way of looking at the tetrahedron that makes it almost appear like a square. And then if I do this other view here with the vertices touching, well, I could have one tetrahedron facing up, and this would be a flat face here with the dotted line on the other side. And this would be the flat, the 2 sides of the tetrahedron. And if I join both of those together, well, this is your classic Merkaba shape, which has the 2 interpenetrating tetrahedron. I've depicted one in blue and red here. So we don't see the red vertice on the other side, but we see the blue one poking through here. And that is now fitting inside this cube. So in each cube, there are 10 tetrahedra, and there are 5 cubes in each dodecahedron. So that means there's 10 tetrahedron in the dodecahedron. So let's just talk about what this Icosa Dodecahedron is when we just look at it as being made up of an internal geometry. The Icosa Dodecahedron is a really cool form because it's actually made up of the 5 compound of the octahedron. So if the dodecahedron is made up of the 5 cubes, the Icosa Dodecahedron is made up of these 5 octahedrons. So we have one view of the octahedron. Now remember, this vertice right in the middle is projected towards you, and the other one on the other side of the sphere would be away from you. So it has six points, and of course that would fit right over top of the, providing those vertices of the Icosa Dodecahedron. Now we're not too used to looking at an icosahedron like the octahedron like this, but this would be if it's just tilted at this right angle, this angle here, and you would kind of see that the blue line in the back, the light one, is kind of see-through X-ray vision, and this is the octahedron how it would look. Now I attempted to, I did. I put the 5 octahedron together, but you'll really only see 3 in this view, this orange, the red, and the blue one, because the other 2 octahedron are directly behind these other ones here. So they're kind of blocked by that view. But there's 2 vertices here. There should be 2 directly behind those spots, which would give you the 5 vertices of this Rhombic Icosahedron. So, I was thinking creatively around this throughout the week here. And, I decided to bring in kind of the esoteric Greek way of just the way of thinking about the elements in relationship to our different forms. So, I was seeing that the dodecahedron here is containing, these vertices are containing the fire, the earth, and the ether, because we've got the tetrahedrons that are connecting to the black vertices here, or actually here, the red dots. I've changed the color from the black to the red. So we have these red dots here, which are they're tripling as vertice of a dodecahedron, vertice of a cube, and a tetrahedron. There isn't really like an internally structure to the water or the icosahedron. It's just these vertices are the blue dots. So we have these 12 icosahedrons, so we have water. And then the air, because remember, the rhombic cube, the rhombic Icosa Dodecahedron, I keep saying rhombi, sorry, the Icosa Dodecahedron is made up of a compound of 5 octahedrons. So on one side, you've got the dodecahedron with the compound of 5 cubes. On this side, you have the compound of 5 octahedron, creating the vertices for the Icosa Dodecahedron. Well, of course, the octahedron was always considered in relationship to air. So we have these 30 vertices, which are these white dots, which are the contributing members of the air spots. So, just in my dreaming mind, I was like, wouldn't it be awesome that, on our Earth here, all of these associated points, here would be the air one connected up to the pyramid, octahedral pyramid structure, which, also has a relationship to fire as well, the pyramid, the fire in the middle. But I was like, wow, this, I don't know if any of you have seen Airbender, Last Airbender, the Avatar. Well, on their little map there, they have the 4 elements, right? And they have different shrine sites throughout that they're kind of visiting, that are kind of caretook by these different communities that recognize sacred spots on their Earth. And each of them have a kind of contributing point on Earth to a kind of energy that it's associated with. And I was like, what a cool map, because I'm not just making this up, I'm basing this on the underlying geometries that, I just pictured in my mind people of Earth coming to these different spots with kind of the fire, the water, the earth, the air, the ether on their minds and energetically enlightening our Earth or putting energy into our Earth to activate these Earth grid spots with a kind of focus. Because the beautiful thing about these Platonic solids that are each represented in these forms, right? Because we have all 5 Platonic solids, is that each of them have kind of like come into balance here in terms of all being, the vertices are all touching the sphere of root 3, 1.732, at least on a 1-inch cube. Of course, the Earth is a lot larger. But I'm just thinking about that root 3 measurement based on the dodecahedron. All the Platonic solids now, all the vertices are all harmonized. They've come into balance. And what type of effect in our planet that would have, even if the people of Earth here managed to focus our attention around these locations with that intent, what would happen? I'd love to find out. But anyway, that's just a little bit of speculation of these underlying vertices of the and how they're related to the structures that are underneath the vertices that are providing the surface points. And there may be some link to our planetary spiritual evolution in relationship to those 5 harmonized Platonic solids. But, you know, I continue to take it further here in my studies, and, you know, I decided to, because we know we have the octahedron and we know we have the cube, and both of those are touching the outer edge of the vertices here. Well, we could just kind of combine that as one form, you know, and it just so happens that when we do that, that becomes the Tetraxus Hexahedron in its biscribed version. So the biscribed version is on that page that I showed you, the web page of D. Makuni's site. So that's another one of the biscribed versions. So now we have 3 of the biscribed forms, including all the Platonic solids, which are 5 Platonic solids. And we've added now 3 other biscribed forms through the study of putting everything with the vertices touching the sphere. So the Tetraxus Hexahedron is a form that I have always called the soul star when I look at it with the inner vertices, with the inner octahedron being shown as an octahedron rather than the square. So this form has always had a special connection to me. But I've always recognized that, you know, the octahedron within the cube could either be down inside the cube, or picture taking a breath, and as you breathe into your cube, that octahedron edges expand out, and as you do that, it's passing through various points until it reaches a straight line with the outer edge, which would then be the rhombic dodecahedron. But until that point, it's going to pass through a phi relationship, a root 3 relationship, and then into the 2-inch relationship all the way the whole length. So that'd be 1.618, 1.732, and then 2-inch till it gets to the rhombic dodecahedron. Now visualize this kind of as like a breathing from the cube to the octahedron. So a while ago, I showed you this form earlier. I made this biscribed version of this soul star version, Tetraxus Hexahedron, because just on my own studies of this, I was like, why don't we just make all the vertices of the octahedron and the cube just all touch the surface of a sphere? Like, why have them not touch the surface of a sphere? I'd like to put it in a sphere so all vertices touch. And when we do that, the cube edge, if it's a 1-inch cube, has a root 3 internal diagonal. Now I'll just make the octahedron have a internal height of the same 1.732 root 3. So it's kind of enlightening to me to find out that, yes, these are biscribed forms, and it's only a handful of forms that you can actually do this with, those 4 forms plus their duals. So, you know, I did that with this view, and then there's the second view down here, which is that angled, you know, the other view of the cube. Now remember, this doesn't look to be like the same size as this cube, but these edges are the same because all you have to do is just rotate that over, and then you get the full length of the cube. Just if you have a 6-sided die in your house, just play around with it, looking at it from different views. So here's the same octahedron. I put those 2 together, and now I'm able to create this second view of the Tetraxus Hexahedron, which for me was just very cool to see it from this view, because the majority of time I've been working on it, looking at it from this view. Okay, so we could kind of just say, like, the Tetraxus Hexahedron and the Icosahedron will create the 5 of these Tetraxus Hexahedrons, and the Icosahedron will create that 120-sided form. But, you know, as things keep, you know, percolating, escalating for me as I studied this, you know, I was like, okay, I created another form a little while ago that, you know, I didn't realize it at the time, but it's another biscribe form. So on my own volition, before I even knew anything about biscribe forms, just following my intuition with my studies, I created this little biscribed form because in that other video, Sacred Geometry, Unified Field or something like that, I was describing the Dystacus Triacontahedron in there because I realized that there's an octahedron. If I put a cubeoctahedron within this form, it's going to inflate this upper side, and I could put that so all those vertices would touch as well. And just so happens, yes, there is a Dystacus Dodecahedron, which is also biscribed, and that has 48 faces and 26 vertices. So this is the cubeoctahedron. These little triangles here, they're sloping away. This is pretty much like a flat plane here. So it's just a plane through the middle. This plane is coming towards you, and the plane that's associated with these vertices are straight through. And then we've just connected those sides. But when you combine that with the Tetraxus Hexahedron here, so we link those together, what that's going to do is it's going to raise up that frontal surface of the cube. It's going to split that distance there and now create another vertice, which then will create these 48 faces all the way around. Now, this is all leading somewhere. I wasn't just doing this for fun. I knew that I was going to be able to link this together with the 120-sided Dystacus Triacontahedron, but it took me like a day and a half of working with the mathematics and in the drawing programs and trying to figure out how I could work this out with sacred geometry, which is very tough to do with the regular sacred geometry techniques. I had to pull into a real bag of tricks that I didn't even know existed for me to figure out how to draw these cubeoctahedron at this scale, at this size, so that it would fit, because I needed to figure out how to, this is easy to draw, but once you draw it like this, at this angle, how it integrates with the rest of the drawings, because what we need to do with this, so this is the cubeoctahedron tilted, connected, and here is with the Tetraxus hexahedron here, which then creates the 48 faces from that view of the Dystacus Dodecahedron, biscribed. So, you know, what I had to figure out what to do was, okay, well, the real form that we need from that is not the Tetraxus hexahedron. We don't need the cube and the octahedron. That's already part of this Dystacus Triacontahedron. But what I do need is the cubeoctahedron. I need to get 5 cubeoctahedrons. And I know this looks like a complete mess of a drawing, and it was a mess to figure out how to draw 5 of these. Because like I said, I am doing this manually. I don't have just a program that spits it out. I've got to figure it out by drawing all the lines and connecting the points, and I've got to draw it 5 times to figure it out how to put it in there. But these are the 5 cubeoctahedron that are all overlapping one another, and then that's going to link up with the Dystacus Triacontahedron, because all these 5 cubeoctahedrons, now remember the cubeoctahedron, which I didn't explain, is pretty much halfway between a cube and an octahedron. If you truncate the octahedron and you truncate the cube, then you get this cubeoctahedron. So it could either be turn into a octahedron, or it can turn into a cube. But that then added a bunch more points to this. So let's just zoom in so you could take a closer look at some of those vertices. So these were the initial connect the dot pattern, and I didn't know what pattern would represent when I put the 5 cubeoctahedron in there like this. But I added 60 more, so I added up to 122 vertices, and then it created this form when I connected the dots, which has 240 faces. And But before we get to that, what happened here was that the cubeoctahedron vertices actually created another smaller pentagon shape inside the larger pentagon that was just a regular dodecahedron. It created a little one here, a little pentagon shape, and it created that 12 more times because it created one on this side, it created one on this side, it created one in here. So those are all mirror images of one another. So we've got 1, 2, 3, 4 here. We've got 4 on the other side. And then, so we got 8, and then we have one up here, 9, 10, 11, and 12. So it created this little mini pentagon shape all the way around here. So then I was just now like, okay, let me just connect the dots. And I came up with this. And this is the first image that I showed you at the very beginning of the, that I stylized with coloring it in and shading, etc. So, the way you can look at this here is it's really a pentagonal surface right here, one pentagon. And then it's got a star in it, 1, 2, 3, 4, 5. And then those vertices that were from the cubeoctahedron actually provided, the 5 cubeoctahedron, provided the inner vertices of the stars shape. So I created this curved pentagon and pentagram shape, which then has each of the little segments. So these are these little kites of the star shape, right? And I haven't done all the mathematics to figure out if that's a perfect golden triangle or not. I'd like to, but it's tricky business to figure this out. But I have 1, 2, 3, 4, 5. I got another 5, so I've got 10, and these are each subdivided into 2. So I've got 20 units within each of these shapes, 20 little triangular faces of different sizes. Now I know they don't all fit to like all the same size. We have got 3 different size pentagon, 3 different component triangles on here, but I wasn't really concerned with that because it was really what the underlying geometries and what they build out would look like. So that's 240 faces, the 20 by 12 to 240 faces all the way around on that there. Hold on a sec. 20 by 12 all the way around. Just wanted to double check. I'm not too quick with math. I'm a little slow with all this, but it makes me double check things multiple times. Let's see here. So then I got back to thinking about Buckminster Fuller's great circles again, because then I wondered, well, how many great circles have I added up to? And I'm pretty sure that I've done all this correctly, but I'm doing the best I can with the technology I have and the visualizations that I do. But it appears to me that this will work out like this, because with these Dystacus Dodecahedron, because now remember, I'm going to take 5 of these and I'm going to add them to this previous form here that I have of the Dystacus Triacontahedron. So we're adding a few things together, but some of these lines in here are part of this form. So for instance, if I take this, because there's 9 great circles in this Dystacus Dodecahedron. So if there are 5 of them in there, there'd be 45 circles, but I can't just add the 45 to the 31 because that's not a correct way of looking at it, because I'll show you that the blue ones here already overlap with this vertical and horizontal circles that just look like a cross and the outer circle. So the 3 of them are being used there. Now I know this is a kind of pitiful looking drawing here, but it's the best I could do trying drawing these arcs, but this is 9 great circles that are, here's 1, 2, 3, these central ones. There's another 1, 2, 3, the blue ones. And then the outer one, 1, 2, and then this one is looping around this way, it's 3. So there's the 9 great circles. And now if I overlay it on the 31 great circles, I could see that 3 of those are also contributing to these vertices over here. But these other 6 are not contributing to it. So 3 are contributing from each one. So the way I kind of worked this out, the 3 of the 9 are contributing. So that means that, you know, there's 6 left over. There's 15, so 15 total of these 5 forms. 3 times 5 is 15. So 15 of this Dystacus Triacontahedron are contributing to all the circles, great hoops of this tricontahedron form, Dystacus Triacontahedron form. So those are all contributing. So that means that we have 30 circles left over of this, which will then add to the 31 great circles, which were the original form. So we have 61 great circles total. So I've added Buckminster Fuller's 30 great circles to the 30 new ones that I've added. So now we've got 61, because this one is not including the dodecahedron circles and the 10 from that, as well as the other 6 from the Icosa Dodecahedron. So that's why we have 61. So I believe we just inflated Buckminster Fuller's 31 great circles to the 61 great circles. And here is my another kind of little messy drawing. You know, it looks like someone wound up a ball of yarn, but because I'm just trying to do the best I can, drawing out, connecting the vertices as we go. But I believe this has got the 61 great circles in here, and I'm looking forward to someone with some more technical skills with other programs that can draw these out, first to verify and test that out to see that if I'm on target with this, and as well just to see a better, tighter version of this. But this was me kind of following out and overlapping the vertices, like this white one here, the white vertices, that should have the Icosa Dodecahedron should go right through the middle of that. Of course, you could keep subdividing all these little spots. I don't know if I'm going to do that, but I think I'm pretty satisfied with 61 great circles at this point. A new form here, like I said, maybe it doesn't meet the criteria of the forms that would be on a page like DM McCooney's, because it doesn't have all the triangles, or three different size triangles. To me, that doesn't really matter much, because I know when I put this over the Earth grid, it's going to start to give me some new vertice spots that were not on there, so I can add in additional vertices. As well, it's going to give me the primary vertices. And it's just a neat way to visualize and look at, well, where are these other little pentagons that are here, this star shape that's within the bigger one, where are those vertices going to line up? See, one right here of this little pentagon already is on the island of Madagascar. So I believe that there's some other research that we could do, and I do think that there's maybe something to thinking about how these vertices are in relationship to the underlying octahedrons, cubes, tetrahedrons, dodecahedrons, cubeoctahedrons that are linking to these sites, and thinking about how this is not just math and geometry, but it's about us awakening in relationship to the Earth and waking up our sacred planet with us consciously being aware that this is a sacred planet, and through the act of understanding our relationship to our place, not maybe through this or maybe through other ways of knowing, brings us into greater harmony with the planet and with one another. So here is my stylized version of that, just colorful way of looking at it, which, I never thought I would be creating something like this. getting into sacred geometry, but I'm pretty fascinated that I ended up here, and I'm looking forward to, you know, continuing to provide more interesting, great content. I continue to revisit everything that I've done, you know, as I've been going along, creating forums like this that I don't understand at the time why it is I'm doing biscribed forms, that somehow it is all leading and guiding me in a way towards a future discovery of how that will already relate to what I'm finding. So, you know, anybody who's involved with sacred geometry, every little doodle, every little form, or everything you make, just keep it, and it's always part of a bigger picture and a bigger puzzle that's revealing to you more understanding and relationship to this material, and how it relates to you in connection to the macro and the micro. So yeah, I hope you enjoyed that video. Let me know if you've tested that out and explored it a little bit more. I'd like to find out if I'm on target with some of this. And I have to think up of some sort of name of the new 122 vertice form. So I'm looking forward to any suggestions on that. And anyway, yeah, thanks for watching and have a great day. Much love to you, and I appreciate your time.